Hello everyone. Proceed to our next chapter, chapter 4, application of optoelectronic devices. As a topic overview, we're going to start with the visible light communications, followed with water or air purification, agriculture, and horticulture, and also fisheries. Visible light communications VLC. To overcome the drawbacks of RF communication systems, it is imperative to design and improve new communication technologies that we have. For communication that occupy the spectrum of 380 nanometer to 750 wavelength, corresponding to a frequency spectrum of 430 terahertz to 790 terahertz, VLC has a large bandwidth and also it has a no health hazards, and VLC receiver only receives signals if they reside in the same room as the transmitter. It has the immunity to security issues. VLC light source can be used both for illumination and communication, which saves the extra power, and also VLC is one of the promising candidates because of its features of non-licensed channels, high bandwidth, and low power consumption. Potential applications for VLC. The first one is Li-Fi. The Li-Fi uses a visible communication to provide high-speed internet up to 100 gigabits per second. Second one is vehicle-to-vehicle communication. Vehicular communication for lane changing, for example for warning, pre-cache sensing, and traffic light signal violations to avoid accidents. Robots in hospitals. In areas that are sensitive to electromagnetic waves, such as aircraft and hospitals, where the radio signals interfere with the wave of other machines. And the fourth one is the underwater communication. And finally, for the information displayed on signboards. These applications requires a communication with a low latency, which is provided by VLC because of its high bandwidth and easy installation due to the existing presence of vehicle lights and traffic signals. Challenges and solution of VLC. The first challenges is the interference, which is the ambient light sources, and of course the interference between these two existing VLC devices, and of course the integration of VLC with existing technologies such as Wi-Fi. Standardization VLC is necessary. Four standards are developed that include Japan Electronics and Information Technology Industries Association. So for example, that VLC standards that are available now is JETA CP 1221 and until 1223 and IE 802.15.7. This is only for MAC and PHY layer that are defined for short-range communication using visible light. In 2011, Harold Haas was the first to coin the term light fidelity Li-Fi term. Li-Fi is a high-speed, bidirectional, fully connected, visible connection, the light wireless communication system, and is analogous to Wi-Fi RF frequency. The Wi-Fi signals have the problem of interference with the other RF signal, such as its interference with the pilot navigation equipment signals in an aircraft. Li-Fi also lends support to the Internet of Things (IoT). A speed up to 100 gigabit per second is obtained using Li-Fi, which is 250 times more than the speed of superfast broadband that we have now existing. So vehicle-to-vehicle communication, due to the presence of the vehicle and existing light traffic light infrastructure, high priority applications which are including the forward collision warning, pre-crash sensing, emergency electronic brake lights, lane change warning, stop sign movement assistance, left turn assistant, traffic signal violation warning, and also a curve speed warning. This is an example of a diagram that shows the application of vehicle-to-vehicle communication. All of the high priority applications require reliable reachability with extremely low latency. Due to the extremely low allowable latency in the vehicle safety communication, a high speed visible light communication system like Wi-Fi can be used actually. An outdoor VLC system using a controller area network CAN was proposed to and the backlights and headlights were used in the proposed system for the communication of these vehicles. Underwater communication. RF waves does not travel in sea water because of its good conductivity. Untethered remote operated, for example, vehicle, for example, a trough is another application of the VLC. Three different jobs that can be performed using this kind of communication of aircraft, including the observatory maintenance of the oceans and deployment opportunity from the ships. So the first diagram here shows that the communication of the aircraft using the optical channel to fix infrastructure of the sea on the seafloor. And then the communication is achieved by aircraft using a channel with a ship-based relay infrastructure. And then the communication of the outro using the low bandwidth underwater sea communications. And you can see here. Hospital robots. In hospitals, electromagnetic wave sensitive areas such as MRI scanners exist. They are likely to switch to VLC because it will not interfere with the radio waves of the other machines. So this is an example of a hospital robot called HOSPI. This was used for transportation in hospitals. The control system enhancements in HOSPI were made using VLC installed in a building and navigational sensors around the robot itself. So you have the security camera here, the VLC receiver, and also the touch display for the control management. So of course the key one is the battery and controller, and we have the storage compartment and also a laser range finder indicated here. Following with the next one is the information of broadcasting signboards and ID systems. This is an example of the system that was mentioned. The signboard actually used for transmitting data as was described. Okay, so each of this signboard, for example, the digital signage display and internally illuminated signboard, they transmit the data from these boards to our receiver. Okay, for example, here is the phone that we use. So visible light can be used is in this kind of application too. And second one, in terms of the ID system for a different places. For example, here this is the handbag here, and we have the LED spot lighting, which is indirect lighting. Uh, this can also be used in a different places such as building and also subways, similarly to the visible light. Okay, this type of ID system can be employed in subway or even in airports too. So for this type of signboard, this can use in various locations, airports, museums, and hospitals, and as you can see here, etc. And mode of verification. So the properties of UV, we have three types of UV, UVC, UVB, and UVA. You can see the wavelength difference of each of the UV. Okay, so from our sun, we have all these three of UV and with a different UV range. So as for UVC, they only limited till here, and UVB until the Earth. However, UVA is until the deep sea level. And the difference between UVC, UVA, and UVB, it never reaches the Earth because the ozone absorbs it, and not usually considered as a risk for skin cancer. And can found only in man-made sources such as mercury lamp and working torches. And it is used for old school tanning beds. For UVB, this aka the show wave light, the chief cause of reddening and sunburn that we have is tends to damage the skin's top layers, strongly linked to cancer, damages the skin DNA, burns this unprotected skin in approximately little less than 15 minutes. Intensity varies by season, location, and time of the day, of course, in summer. And of course, Malaysia, we have this UVB all around the year. For UVA, aka the long wave light, it accounts for the 90% of the UV radiation that reaches the Earth. It can be used in standing beds, penetrates the skin's second layer, plays a major part of skin aging and wrinkling, contributes to some types of sun damage, and also we can penetrate glass and clouds. Deep UV LED. This is an example of a structure of a deep UV LED. The material that you use for one of the famous material that we use for deep UV is argon base. So deep UV LEDs we can use as a disinfection, sensing, water and air purification, biomedical, general lighting, and etc. UVC for water purification. So with this type of device, we can put it in the UV LED chamber. So to this water purification, we can increase the quality of the drinking water at home. However, the most promoted areas that we want to focus on throughout the world is in the developing countries, that third world countries, and in a disaster areas where the water sources is very difficult. And the first stage is actually the water will pass through a normal filter. There's a lot of filter existing now, charcoal filter, and, any types of filter, right? And then after the filtration system, however, it is still a probability of a harmful microbial pathogens existed in the water. So we have to go in the stage two, which is the UVC LED, and then this a UV exposure with a UV can sterilize these microbial pathogens that unwanted, and then directly to the source of water. So this is one of the unique application of UVC LED. Light emitting diode LED at a geometrical UV radiation, which is less than 300 nanometer wavelength. This is UV LED. These types of products have been increasing the output power and extending the lifetime, and some are even challenging in terms of reduction costs. In the seams, the past prediction based on what is called Haigh's law was too optimistic, unfortunately. But the situation can be varies and has been changing so rapidly. However, you can see here now that UVs are on track for the real application and practical application. So this is the light output here, lumen, and also the cost per lumen per USD. You see the projection here. However, actually this is the cost per lumen here, the decrease and the brightness increases. However, the cost for the white LED brightness here, and also the cost per lumen for what so here. So this is the actually the Haigh's law here, the straight line. So there's a difference in terms of here. So now it is nearly similar with the predicted Haigh's law, the tradition now we have. So UV-6 LED also is used in a water purification. So for example, before in the aquarium, and as you can see here, water becomes better, and this eliminates of these kinds of microbial pathogens and bacteria. So this is an example of a normal UVC LEDs versus the UV mercury lamp. So the advantages of UVC, which is including does not require warm up, so we can have a power consumption reduction, and also does not damage and shorten the lifetime, and mercury free, and of course mercury is hazardous, and it is available in smaller size compared to the lamp, and it has a better lifetime. Of course it is LED, right? So UVC is mercury-free, as I mentioned earlier, and a small size, warm-up-free, resistance to frequent on and off sky cycle, and selective in peak emission wavelengths. International trend to reduce or strictly controls the use of mercury in general promotes this kind of invention of UV LEDs. This can be achieved using UV LED and it is mercury free. More specifically for water treatment, the barriers against the mercury leakage, particularly at the severe incidents, are no longer needed if you use UV LED, which also contributes to a overall simple system design. UV LED composed of a typical size, a 3 to 4 millimeter for single package, which allows flexible design and all modification throughout the reactors. Several studies has been developed with unique types of UV LED apparatus for the purpose of disinfection system. So water purification, as mentioned before, does not require blah blah blah, and not shorten the lifetime compared to the mercury LEDs. And these features allow an intermittent operation, which is preferable for on-demand use, such as POU, which is a points of use and also points of entry POE water treatment options. And also good for systems with a high fluctuation water and demand, such as a community-based water supply with as a limited connection, as I mentioned earlier. So POU and POE applications has been growing in cities developing countries, which a very high concern of this problem. So the cost here is an issue, but it is not forever. Scientists has done intensive field surveys and water quality and water use behaviors in Asia, which is including Hanoi and Vietnam and also Kathmandu in Nepal, and noted that rapid urbanization resulted in limited access to centralized water systems and urges people to use decentralized water sources such as unprotected dug well or even the private water vendors. Water from sources is occasionally, of course, contaminated with microorganisms. This is unavoidable. Okay, so moreover, in centralized public water supply systems, water quality deteriorates with a significant decay of residual chlorine in the distribution network and rooftop storage tanks, highlighting an apparent need for this type of POE and POU treatment in the household. In fact, people are taking several coping strategies, including these types of installation. A survey conducted that 76% residents in central Hanoi were taking POU treatment at home, while POU apparatus in use were not working against the barrier microorganism, unfortunately. So, for example, this system, even though there's a lot of filtration, yeah, but we cannot prevent these types of contamination. However, the UV LED can be smart add-in option for these such systems. In Japan, health-related incidents associated with drinking water in 30 years were mostly associated with disinfection failure. If you have been to Japan, so Japan is unlike Malaysia, we can drink directly from the tap water. Okay, so based on the study, there's a 44% which was happening in at private, including community well owned and also small water systems. So most of the contribution is the small private systems and the supply tanks. This is unknown. Large public waterworks, small public waterworks, and private systems here. So the simple and effective, feasible and sustainable measures are needed at a small systems because they contribute large amounts here, 44%. Uh, However, and financial resources are limited for these individual systems to be designed for operation and maintenance, not by skillful engineers, but the use of their own responsibility. So this was reported. Statistic was reported from 1983 to 2012. To promote both research and practical applications, standardization of fluence, which is the dose, determination for UV LED systems is very crucial and very much needed. The question is how to determine the fluence of LEDs having various emission spectra with different peak emission in a comparable manner for conventional mercury-based UV lamps. Biodiversity and the concept of reduction equivalent dose RED are basically valid for UV systems, while some modifications are still needed. Currently, some of the people consider LED as monochromatic light source, while the others take it as a polychromatic, resulting in a mismatch of protocol for the fluence determination and particularly on the wavelengths conversion. Moreover, UV-based technology for water treatment are standardized at 253.7 nanometer wavelength, but the actual rationale to do so far for the UV LED is still unclear. This kind of references may not be needed or even scientifically correct for the UV LEDs emitting out of this particular wavelength. Further discussion is very much needed. For more practical applications, just thinking of the replacement of conventional lamps of mercury with UV LED is not expensive and quite attractive. UV LEDs are expected to open the door for new applications, which eventually stimulate the whole market of UV-based technology. A paradigm shift is still needed. That is all for today. Thank you, everyone, and have a good day.